Alright, last little bit of section 2.4 here. We've done addition, subtraction, and multiplication, so that brings us to division of complex numbers, but there's something that's going to be a little bit different here with division. And one thing is this: we've got to run into something that we call complex conjugates. And you guys have done conjugates before, but we have to see if we can still make this work out in terms of complex numbers. Now, we have to think back a little bit, probably back into your second year algebra, where we ran into some things like you maybe did some work on a problem and you ended up with a problem that had a solution that looked like this. And we said that that wasn't considered simplified because we couldn't have a radical on the bottom. So we did what we call rationalizing, and we multiplied by the square root to get 2 square root of 3, and on the bottom, square root times itself, simplified down just to the value under the square root sign. So that was kind of the idea there. Now the idea with complex conjugates go this way. I could have 2 plus 3i on top and 3 minus 4i on the bottom, and if you remember I stood for square root of negative 1, which means this would be the same actually as 2 plus 3i all over 3 minus negative 16 under the square root. Can't have a radical on the bottom. Well, unfortunately here it was nice because we had just one radical. You could take it times itself and it would cancel. Here I've got a minus sign, so I can't do that quick little shortcut. So that's where this idea of complex conjugates comes in. So let's do a little review here real quick. Conjugate, if I had some value that was a plus bi, the conjugate of that, we just reverse the sign for the imaginary part. So these two are conjugates of each other. And since we're talking in terms of a complex number and another complex number, they're complex conjugates. So little review with this: 2 plus 3i, its complex conjugate would be 2 minus 3i. If I had just 3i, which is positive 3i, negative 3i wouldn't be its conjugate. And if I just had 5, which would be the same as 5 plus 0i, well, 5 itself is its conjugate. So, with that being said, let's see how we can work this out and what it has to do with making these things go away. So first of all, let's take a look at the generic setup here. So let's just do an a plus bi and an a minus bi. Alright, a couple things that we can do with this one. One, we could look at this just like FOIL and say, alright, first times first, a squared. Outside times outside, negative abi. Inside times inside, positive abi. And then last times last, negative b squared, I squared. Well, we got opposites here, so they're gone. And I squared is negative 1, and negative times negative becomes positive. So we just get a squared plus b squared. So our shortcut for this, anytime we multiply conjugates, if they're complex conjugates, we're going to take just the a part and the b part, and we're going to square both of them, and we're automatically, because of this negative 1 taking the place of I squared, going to turn this into a positive. So if we did a couple shortcuts here, 2 plus 3i and 2 minus 3i, shortcut says take 2 and square it, take 3 and square it, add them together. So in this case we would get 4 plus 9, or 13. Notice the i's disappeared, which is the same as having a radical disappear. So we're going to take that in and throw it into our division problem and show you how this simplifies or basically rationalizes the bottom of the fraction. So let's say they give us this. 2 plus 3i all over 4 minus 2i. Now it's not necessary to do the parentheses, but I'm going to do it just to show it's a complex divided by a complex. As long as I've got that I on the bottom, I have to find a way to get rid of it. Well, we just proved that if we do a complex conjugate, it's going to make the I disappear. Now we don't care about the top if that still has an imaginary part or not. So on this one, the top, I would probably just do normal FOIL. So first times first, 2 times 4, outside times outside, 2 times 2i, inside times inside, 3i times 4, and last times last, 3i times 2i, 6i squared. Now on the bottom, a shortcut for conjugates, first one squared, second one squared, and add the plus. And again, I don't have to do the I, because by doing I times I is I squared, that's going to change this from a negative to a positive. So we can just save that step. Now up here again, I squared is negative 1 times 6 is negative 6, plus 8 is positive 2, like terms. 4i plus 12i is 16i. On the bottom, 4 squared is 16, plus 2 squared is 4, which gives me 20. Now once I get to this part, I've got 2 options. One of them would be split it into fraction with like denominator, and then simplify that. So this would simplify down to 1 over 10 plus, and here I can divide 4 out of both of these and get 4/5 times I. Now a lot of people like this because it looks like a plus bi. So we're working with complex numbers, we can write our answer as a complex number. Now other people would just take this and say 2 plus 16i over 20 and say, hey, I can divide this by 2, this by 2, this by 2, and then they would leave it as 1 plus 8i all over 10. Both of them equivalent answers, just written in different forms. And whichever one you decide to use maybe depends a little bit on whatever problem that you're working on at the time. So that's our section with complex conjugates and how they help us out with dividing complex numbers.